Well, hello class, good job today. Well, today we worked on SimCalc and some applications of how speed and distance interact and how to find out, given how far you go over a period of time, it can tell you what your velocity is and vice versa. So one example that we looked at was what happens when you're going at 4 meters per second for 8 seconds. So we said, we went 32 meters per second. An interpretation of this is you're just kind of strolling along for 8 meters per second. You're kind of going for a jog. You're having a good time. But the geometric interpretation of this, it makes sense. It's intuitive that if you go at 4 meters per second for 8 seconds, you'd go 32 meters. But also, you see this is a box that's a height of 4 and a width of 8, which we also know has an area of 32. And it's very interesting. Another thing you'll notice is that if we have meters per second here, instead of writing it like you would say in common language, then we'll notice that if you multiply the height and the width, you actually just get meters, which is exactly what we'd expect, isn't it? Isn't that nice that you can use that as a check? That's actually pretty crazy. And then we looked at a few other examples, such as, okay, what happens if you're really just going for a stroll? You're smelling the roses, and then all of a sudden a bear's behind you. What happens? Well, then you speed up to 6 meters per second, and you're really going at quite the clip. So from second 0 to 4, you're going about 2 meters per second, and that gets you 8 meters. Now, how do we know that? Well, one, it's just kind of common sense. You go 2 meters per second. For 4 seconds, that's going to be 8 meters. Another thing is that you can use a geometric interpretation. Now notice that each of these boxes essentially represents 1 meter that you've gone. That's pretty cool, huh? So we could actually just count up all these boxes. Fascinating. And then up here, we go a little farther, and it turns out that here you also go 32 meters per second. So that might be intuitive because 2 and 6 average out to 4. 4 being how fast we went in the last graph. But it also might be intuitive because you'll notice that here, remember this is where the box was before? So we notice we're actually losing out on this piece, but we gain it here. Okay. Now let's say that it's not quite like that. So we're saying, well, we're gonna start out like at a real measured pace and gradually go up. Maybe we're on the treadmill and we're thinking we're just going to go boop, boop, boop every couple seconds or every second or so and increase the challenge. Well, it would look a bit like this, right? And this is a little more challenging because we have to work with halves. But, we can do it out. During the first second, we go, half a meter. Then we go 1.5 meters. In fact, it turns out to be pretty easy because the speed at that second is exactly how fast we go. Once again, about what you would expect. If we go 3.5 meters per second for 1 second, we go 3.5 meters. All right. So let's take this one step farther. Okay, this is a discrete changes each time, right? But what happens if you just want to do a gradual ramp up? Like, in other words, what if there were mini steps? In other words, you didn't stay at one speed for a very long time. Let's think for a moment, what would that look like? That's right. We hearken back to the very end of our activity where we find the triangle with the same area. It would look something like this, wouldn't it? And so this is almost exactly what it would look like if you just had, we'll say, infinite steps. So what happens if your staircase has, you're going up a staircase that has 1 step, right? That's one really steep step you have to take. What happens if you've got 2 steps? Well, that's a pretty steep step if you want to get to the next bloop, bloop, you have to take, man, you'd have to be quite the jumper, wouldn't you? Here, pretty reasonable, but what if it has infinite steps? Think about that. What would a staircase look like then? It would really just look like a slope. And that's basically what we have here. Now, we also notice this is also intuitive because it's got the same area, And one thing I will ask you, one thing I'll leave you with this, is how would you know that it had the same area without doing math? Just doing it geometrically. How would you know? Start with asking yourself, just by looking at it, without doing any calculations, just using what we know from geometry, how do we know that this triangle has the same area as this rectangle? And how can we use that same argument over here? Okay, great. So can anyone tell us what our big revelation is? Well, if we have a velocity graph, the area underneath that is the distance.